Thank you very much for the introduction. I'm very happy to be invited to give this talk. Unfortunately, I couldn't come in person. I had a last-minute problem, but I hope this will work out as well. The overview of my talk, as the title was mentioning, is about machine learning of electronic charge densities. So I will first introduce this method and then try to show how this can be useful to predict the charge density response in metal electrodes that are in contact with electrolyte solutions. And finally, how we can use these machine learning predictions to accelerate QMMM kind of simulations of electrochemical interfaces. So the kind of machine learning that I do is not very popular, I have to say. Is not neural network. It's called Gaussian process regression. Probably most of you already know what it is, but for those of you who don't, I just try to summarize here briefly. So in this kind of machine learning method is a bit halfway between linear regression and neural network, in the sense that it encodes nonlinearity to a certain degree, but is not as nonlinear as neural network, let's say. So we can start by, what is nice about this is that you can interpret it in a Bayesian sense. So for instance, you can think at your target property F as a Gaussian random variable over the space of your atomic coordinates. So this will be Gaussian distributed with a mean M and the covariance function K. And then from a machine learning point of view, what is interesting is answering the question of finding a new property F conditioned on a set of previous observation of the target properties, so what we call the training set, big F. And so what we want to compute is the conditional probability of measuring F conditioned on this observation, and we can use Bayes' theorem to compute this probability, and it turns out that this is also a Gaussian, and what we are interested in is the expectation value of this conditional probability, which gives you what is the expected prediction of your property condition on the observation previously done. And this is the very well-known formula of Gaussian process regression, where you have your vector of training properties, and then the learning reduces to inverting a matrix at the end of the day. So it is as complex as doing linear regression, but as I was saying, the fact that you rely on these correlation function Ks allows you to include somehow a degree of nonlinearity. So once you have trained your model and you will have your regression weights, you can then build correlation functions K between the new input small x and the set of training input big X, and then you perform a simple linear combination that allows you to predict your target. So the real question in this family of methods is how to compute these prior covariance functions, which we typically call kernel. And so since the space of input is defined by the atomic coordinates, we can think of these kernel functions as similarity measures between local atomic environments of the system. We all know that in these machine learning methods, we work with locality, and so with local environments around the atoms. And so these kernels, in a sense, give you a score from 0 to 1 about how similar are pairs of environments, 0 if they are completely different, 1 if they are entirely equivalent. In these machine learning methods, since it is not as nonlinear as neural network, it's especially important to enforce some physical priors into the model in order to make it efficient. And in particular, a physical property is very important to enforce is rotational symmetry. So as you might already know, is for instance, so if you target the prediction of electronic energies, these are typically rotational invariant properties, and therefore, in our case, we would need to build kernels that are in turn rotational invariant. So, but in my case, as I was mentioning at the beginning of the talk, I'm not interested in rotational invariant because I'm not dealing with electronic energies directly, but I would rather like to machine learn something that is not at all invariant under rotation, like the electronic charge density of the system. So this is, of course, a crucial property of chemical physics and material science, and we have it everywhere. So it would be very nice if we try to set up a machine learning model for this. But as I was mentioning, now the transformation properties of this object are highly non-trivial because it's formally have a continuous scalar field. So we need to understand how to enforce this rotational symmetry within our kernel functions. So in fact, the first question that we need to answer is rather how we want to discretize this continuous scalar field in order to handle a finite amount of numbers. And a possible strategy is that of expanding the electron density on a basis of atom-centered spherical harmonics. So you will have exactly as in quantum chemistry codes where you expand the wave functions on the basis of atomic orbitals, you will have a set of radial functions on the atoms and spherical harmonics and a set of expansion coefficients. So these expansion coefficients C are exactly our machine learning target. And by doing this decomposition, you soon realize that the rotational symmetry that you need to enforce is that of spherical harmonics. In fact, these expansion coefficients will transform spherical harmonics. And in particular, if you rotate the atomic structure, these coefficients will be multiplied by Wigner-D matrix that is what expresses rotations in the space of spherical harmonics. So how we can do that? What you can do is to, and what we did, is to first try to understand how to build a structural descriptor that allows you to encode this symmetry directly. So what we did is to extend the popular smooth overlap of atomic position method, the SOAP method. And this is very famous, but I'll briefly mention. It relies basically on placing Gaussians on top of the atoms and defining a smooth atom density field that you can then cut off around the atom to define a description of your local environment. And once you have this fictitious atom density, you can then combine it in such a way that you can build a rotational equivariance. So for instance, in what I reported here in the last equation is a way to incorporate three-body correlations by also enforcing the rotational symmetry of spherical harmonics. And in particular, we perform a Clebsch-Gordon combination of a pair of spherical harmonic components of the atom density in such a way that the final descriptor will be in turn transforming as the spherical harmonics and at the same time encode three-body correlations. So we called this lambda SOAP. But if you think about it, in many circumstances, you also need to incorporate some information about the system that falls outside the finite radial cutoff that you have defined. And so in many cases, and that will be also the case of electrochemical interfaces, you need a long-range descriptor, something that can capture the behavior from atoms that are very far apart. And to tackle this problem, we developed something that we called LOD, that stands for long distance equivariance, which essentially comes naturally from the SOAP construction by defining an electrostatic potential from this smooth Gaussian density field. So we simply apply the Coulomb operator on top of this smooth Gaussian density, and we define a fictitious electrostatic potential that we can then evaluate once again around the atom of the system to describe its local environment. But the key aspect now is that since this potential is built from essentially a Coulomb operator, you will feel within the environment structural changes that occurs everywhere in the system, even nanometers away from it. So this is very important because In this way, each atomic environment now can be used effectively as a long-range descriptor. And so you can use these structural features and combine them, for instance, with the atom density features in order to build rotational equivariants that are once again three-body that transform as spherical harmonics and have this long-range information built in. So once we understood how to build these descriptors in such a way that mimic the transformation properties of the electron density coefficients, so you see that both the coefficients and the descriptor will now transform in the same way, we can build what we call covariant kernels or equivariant kernels, as you prefer, by taking dot products of pairs of equivariant descriptor contracted in the feature space. And thanks to these covariant kernels, we can now perform covariant predictions of the density coefficients by simply combining these kernels with a set of regression weights that in turn will transform as spherical harmonics. So in fact, the learning problem is much more complicated than that, but I won't enter into the details. Just want to mention that over the years, this ended up in a code that we call SALTED, which stands for Symmetry Adapted Learning of Three-Dimensional Electron Densities. And thanks to this code, we can do highly transferable prediction of the electron density by learning it on a relatively small and simple system and allowing us to perform linear scaling predictions in systems that are much more complex. So I just want to mention that this code is interfaced with a few quantum chemistry programs such as FHI-AIMS, CP2K, and PySCF. And in particular, you can interface the two. You can use Salted in combination with any quantum chemistry code that allows you to have the electron density expanded on a spherical harmonics basis. So this is typically called the resolution of the identity method or density fitting method in quantum chemistry or electronic structure. So we just had tried in combination with these three codes, but in principle, you can attempt also others. So this is it for the machine learning method. That's what I wanted to tell you. And now I want to discuss how this can be useful in the simulation of electrochemical interfaces. So since a couple of years, in fact, I'm trying to study these kind of systems, which we know are very complex because you have the interplay of very non-trivial physical effects, like you will have some electrodes where you have an accumulation, depletion of electronic charge. And then you will have that this charge is screened by the thermal distribution of ions in the electrolyte. And also you will keep the two electrodes and at an applied potential that bias the system. So all these three effects must be taken into account simultaneously. And so this is a perfect scenario where machine learning can be very useful. So in particular, since I started working on this in Paris, I started tackle the problem from a classical molecular dynamics point of view. In fact, here they have a lot of expertise in simulating full electrochemical cells that represent ionic capacitors, where you have explicitly a pair of electrodes that are kept at a constant potential, and in between you will have an electrolyte solution, like in this case. But the problem here is that even though you can tackle the simulation of very large system, the electronic distribution on the electrodes is inherently quantum properties. So it's a problem to try to approximate this with classical methods. And the way they are tackling this problem is actually quite clever, is to use what is called the a constant potential method for for electrodes, which means that you introduce additional degrees of freedom, which are the atomic partial charges on the metal surfaces that can be varied during the molecular dynamics simulation in such a way that the potential difference between the electrodes is kept constant. But of course, this representation is still classical, so it has some limitations. So we would very much like to replace this with something that is more quantum-based, let's say. So when I first started thinking of how to solve this problem, I was just thinking to perform this kind of reference calculations with DFT. But if you think about it, it's highly non-trivial how to impose a potential difference between two electrodes in DFT. And luckily, I realized that you can actually think at this problem in a different way. And they proved, in fact, that performing simulations with 2D periodic boundary conditions where you have a pair of electrodes under an applied potentials is totally equivalent as considering a single electrode where you now have 3D periodic boundary conditions and you apply an electric field along the direction that is orthogonal to the electrode surface. And the key thing here is that the field intensity has to be such that E times the length of the box has to correspond exactly to the potential drop that you'd impose in a 2D periodic setup, let's say. So if you do so, you find that actually the simulations results between the two simulation setups are exactly the same. So why this is important? Is important because from a density functional point of view, it's much more convenient to adopt the latter approach. So to have a single electrode with an applied field. So I started exactly thinking about this approach. And so to start, I was considering a QMMM kind of a representation where you have where you treat quantum mechanically the electrode and you treat classically the electrolyte. And in this way, I can compute with DFT a quantities that is directly related at what these classical methods would simulate by fluctuating the metal charges. So this is in fact my learning target in this sense will be the charge density response of the electrode defined as the electron density of the electrode embedded in the electrolyte solution minus the electron density of the isolated electrode. So I can define this my learning target, and the hope is that we can incorporate this into simulations in order to perform effectively something that is as accurate as QMMM. So to start, I was wondering how if the salted model could actually be used to reproduce this charge density response in an accurate way. And so I started with a toy model where I just took simple isolated slabs of gold of increasing thickness that are put in contact with a classical Gaussian charge. And so I built a training set of charge density responses and trying to learn these with salted using descriptors that are both local and non-local. In fact, you'd expect that this response is quite non-local, so you would need long-range information in this case to capture this non-local effect. And this is exactly what we observed. If you see this figure where I report the predicted polarization of the electrode as a function of number of metal layers. So I extrapolate the prediction in a size regime that is larger than that used for training. And you can see that if I use salted in combination with soap, with a local model, I am not able to accurately reproduce the polarization of the system, while if I use it in combination with a long-range description, such as LOD, I'm able to fairly decently predict this polarization. And of course, when you extrapolate massively, this is not accurate as well, but it's still much better than adopting a local approach. So once this was clear, we started treating something more realistic, such as an ionic capacitor, which is made by a gold electrode in contact with an aqueous solution of sodium chloride 5 molar under an applied potential of 1 volt. And to start, we just considered the classical simulation of this system. So we just generated classical trajectories using MetalWalls. And we wanted to see if we could effectively reproduce the polarization of this electrode using our method. And in fact, we could do it very accurately. You see this parity plot where we reported the predicted polarization versus the reference DFT. And the correlation is very high. And this is in fact reflected in, if you compare the real space response with the DFT counterpart, is the comparison is really striking. So these really work very well. And interestingly, you can see that prediction of the polarization done with the classical approach overestimate a bit this quantity with respect to DFT. So this we also see in the differential capacitance, where you have that our machine learning prediction give a value that is slightly reduced with respect to the classical value. So once again, this is just done on top of classical trajectories. So the interesting question now was if we could use these electron density predictions to actually drive the dynamics of the system, of the electrolyte in particular, by keeping the electrode fixed. And so from a practical point of view, this is not a trivial task, because if you think about it, your electron density response is an expansion over spherical harmonics. And this C in blue will be what is predicted by the method. And so we will need to compute the electric field coming from this charge density response in order to propagate the dynamics of the electrolyte. So in order to do this, we derived a generalization of the Ewald summation method to account for this spherical harmonics expansion. I'm not totally sure the derivation is original. It might already exist, but I couldn't find it. So I might be, I don't know. But the idea is very much the same is very much the same that of the classical Ewald method for Gaussians, where you define a slowly varying component of the electron density that you can efficiently compute in reciprocal space, and then you subtract it from the electron density in order to define a screen charge distribution that instead can be efficiently computed in real space. And so if you do the math, you find that you can then compute a short-range component to the electric field and the long-range part. And I just reported here the formula for the sake of showing them. But this is just to say that this might look complex, but actually all is nice and analytical. So this implementation can be done very efficiently. So you will see that in blue, these are the quantities that will enter the calculation of the electric field, because are the expansion coefficients of the electron density. So once we have done this implementation, we have validated against the DFT, and you can see here for a reference structure where we reported both the charge density response and the electric field, and the gray area represent where the electrode is. And you can see that the agreement is especially good outside the electrode, which is the relevant region for driving the dynamics of the electrolyte. So in particular, we will compute the force simply by multiplying the electric field evaluated at the electrolyte atomic position by the electrolyte partial charges. And we compare these atomic forces with the DFT reference for something like 400 configurations. So you have a lot of atoms here. And we found a super high correlation. So this means that really these kind of predictions are super accurate. And in fact, we had an error on the forces that is as small as 1 milli-electron volt per Armstrong. So these has been implemented, the calculation of the electric field has been implemented in MetalWalls, and then we have been interfacing Salted with MetalWalls in order to run this data-driven dynamics. So in particular, the way it works is very simple. Salted will predict the density coefficients of the electrode that gives you, that are in turn are plugged into MetalWalls that will compute the electric field, will update the atomic position of the electrolyte, which will give back to Salted, and so on. Doing so allowed us to drive the electrolyte dynamics through predicted charge densities. And we achieved a massive speed up greater to 10 to the 3 with respect to QMMM, and the calculation was only about 50 times slower than classical simulations. So I just want to report some simulation results. So we ran simulations both at 0 volt and 1 volt and computed the accumulated charge on one side of the electrode, so the total surface charge, and see how it evolves in time. So we were able to run the simulation for about 3 nanoseconds. And we found that while at 0 volt, of course, both the classical model and that interface with Salted oscillate around 0, at 1 volt, we observed that the result of our simulation give an accumulated charge that is much smaller than what predicted by the classical model. And this is also reflected in a capacitance that is basically halved in the case of 1 volt with respect to the classical simulation. And you can interpret this if you look at the ionic profile at the interface, in this case at the negatively charged surface, where you see that distribution of sodium obtained through our method is displaced away from the electrode with respect to what's predicted by MetalWalls. And this can explain why the capacitance is smaller. Okay, so you also can show differences with respect to hydrogen distributions, but this is not particularly relevant, I think. So yes, so with this I can conclude. I just want to thank Mathieu Salan here at Sorbonne Université and Rodolphe Biemi at INS Paris, with whom I collaborated for integrating Salted with electrochemical simulations. I want to thank Michele Ceriotti and Gigaza Nigam, with whom I started all this machine learning development, Mariana Rossi, with whom I'm currently collaborating in the development of Salted, and then Augustin Bussy and Alan Lewis, who helped me out in interfacing the program with the CP2K and FHI aims. So that's all. Thank you very much for your attention.